Welcome to today's lesson. So basically today we'll be dealing with a very practical question. The practical question that we'll be looking at reads as follows. Calculate the cross-section dimensions of the wooden beam below using the conditions of normal stress given that the limit of the bending strength of the beam is 16 megapascals. So basically this is a very long question, so I'll probably deal with it within the course of 2 videos. So this is how our beam looks like. Our beam looks like this. This straight line here is our beam, and then these are forces that are acting on this beam. We have a fixed point force which is of magnitude 12 kilonewtons, and then we have a shear spread out force which is spread out over a length of 3 meters, 13 kilonewtons per meter. So basically it means for every meter there is 13 kilonewtons that is acting on that meter. And then this beam is held by 2 beam supports at the end. Both of these beam supports are movable, so it means we need to replace them with certain reactions that are occurring within these beams. So for a further illustration or further explanation on what reactions you can use to replace these beam supports, you can check out one of my videos which I recently posted. The main task or our main question today is asking us to find the dimensions of the cross section of this beam. So basically what this means is that when we talk of cross section, what we actually mean is that if we take this beam and then cut it at a certain point and look at the surface that is perpendicular to the axis of this beam, we are going to see a certain shape. In this case, the shape that we've been given the shape of a square. We've been given a square as the cross section of this specific beam. But in other circumstances, you might have a square, you might have a cylinder, you might have a C-shaped or a C-channel beam, you might have an I-channel beam. It basically just depends on the question and the kind of beam that you're having. But in our case, we're having a beam that is shaped in form of that has a cross section shaped in form of a square. So having said that, like I earlier said, we need to replace these beams. We need to replace these beam supports with certain reactions. So in this case, since we are having movable beams can be replaced by one reaction that is directed along the y-axis. What this means is this: at this particular point, I'll put a certain reaction to replace this beam so that it helps in my calculation, because in my calculation I won't be using this beam support, but instead I'll be using the force that I'll determine after I've replaced this beam support with this certain force. But in this case, notice that I do not indicate the direction in which this force is moving or in which this reaction is moving, because I do not know yet. If for example, when you remember statics, in statics we use the equations of equilibrium to determine the forces that are in these beam supports. If it's a negative, it goes in the opposite direction. If it is a positive, it goes in the direction that I initially assumed. So even here, I'll replace this beam support by a certain force which I'll not indicate the direction in which it is moving. For me to be sure in which direction this beam support is moving, I need to carry out a statistical analysis. What this means is that I need to calculate the magnitude of these 2 forces that I've replaced these beam supports with. So in this case, I'll do this. Let me just quickly redraw this beam. I have my beam here. I have my beam, and then I have my force which I've replaced. I'll name this force for now as RA. This is my point A. I'll also name this force, this other force here that I have, as YA. Sorry, let me say this is YB. This will be my point B. And then this is how my beam looks like now. I have this shear spread out force which is 13 kilonewtons per meter. I also have a force here which is 12 kilonewtons. and then the distance, tack, tack, 1 here, 1 and 3 here. All right, I hope it's visible. So basically this is 12. This is how my beam looks like. So let me take you a bit back to statics. When we're dealing with statics, we remember that the three equations of equilibrium are that along the y-axis, the sum of the forces along the y-axis is equal to 0. The sum of the forces, sorry, this is supposed to be sum. The sum of the forces along the x-axis is equal to 0. And then the sum of the moments at a certain point within this beam, for example at the point A, is also equal to 0. So having said that, we can now start analyzing our beam. But when we're dealing with statics, this shear spread force is replaced by a fixed point force. This here is a fixed point force, so we need to replace this shear spread out force by a fixed point force. How do we do this? We need to calculate this fixed point force, which is represented by a capital letter Q. This is basically the product of the small q times the distance. So in this case, our small q is 13 times the distance that it has, which is 3. This gives us 39 kilonewtons. So basically, we can replace this one here by our force q. Our force q is placed midway between these 2 points. So it is placed midway. It is basically half of 3. So our force q here is at 1.5 this side and 1.5 this side. Yeah, so having calculated q, we can now start analyzing this beam. We are having 3 equations of equilibrium, but in this case we do not see any force that is directed along the x-axis. This here will be my y-axis and then this will be my x-axis. But in this case, I do not see any force that is directed along the x-axis. As a result, I'll get rid of this. I'll focus on my y-axis. I'll say the sum of the forces along the y-axis is equal to 0, and then start looking at the sum of the forces themselves. My force RA, I'll take this direction as positive, and then I'll take this other direction as negative for y. So the sum of the forces, I'll look at this force RA. It is moving along the positive direction of my y-axis, so I take it as RA with a positive sign. And then my Q here is moving in the negative direction, so it will be minus Q minus this 12 that I have and plus YB. So to sum it up, this is 39, negative 39 minus 12, I'll get 51. So in summation, I'll have, when we find the additive inverse of this, it gives us positive 51. So I'll say RA plus YB is equal to positive 59. This is my first equation. This becomes my first equation for equilibrium. And then the other thing, I also need to form an equation for the moment. So the sum of the moments at point A, I've decided to take my point here, will be equal to, remember, a moment is defined as the bending effect of a force. So what this basically means is that if I stand at point A, this force that I have here will gain a certain distance. So that distance multiplied by the force will give me the moment. So in this case, the rules here are that for statics, when I'm moving clockwise in the clockwise direction, if the force is moving in the clockwise direction, then it carries a negative sign. So in this case, how do I know whether the force is moving in a clockwise direction or not? I start turning my paper following the direction in which the force is moving. So if you can see, this force here is telling me that it is moving downwards. So I'll start turning my paper downwards like this. This shows me that this force is moving clockwise. If I look at YB, my force YB, if I start turning my paper upwards like this force is telling me that it is moving in the anti-clockwise direction. So for statics, we are saying clockwise is equal to negative, anti-clockwise will be equal to positive. Having that in mind, we can comfortably now say the sum of the forces at point A. This one is moving. The distance from this point that I have to this one is 1.5. Remember, we divided this 3 by 2, so this is 1.5. That is the point at which this Q force is acting. So I'll say, since it is moving in the clockwise direction, it will have a negative sign. So Q multiplied by 1.5. And then I'll also go to my 12. This is also moving in the anti-clockwise direction, so I'll have minus 12 multiplied by the distance that it has. It is 3 plus 1, which gives me a 4. I'll also have this YB. This YB, if I move my paper like this, it is moving in the anti-clockwise direction, so it will have a positive sign here. YB times 5 is equal to 0. I have the value for Q. The value for Q is 39. So I can comfortably say, sorry, my camera has moved a bit. So I can comfortably say that 39 multiplied by 1.5 will give me 39.1.5 will give me 58.5 minus 58.5, and then this will be minus 12 times 4 will give me 48 plus YB times 5. So this alright, so if we divide 106.5 by 5, we are getting 21.3. So basically, what this tells us is that for us to find RA, remember we made this first equation. We made this first equation for RA where we're saying RA plus YB is equal to 51. So having known that YB is equal to 21.3, I can comfortably replace this YB into this equation and obtain RA is equal to 29.7 kilonewtons as well. From this, I have gained positive values for both RA and YB. What this entails is that the directions in which these two forces are moving, the directions in which I assume that these two forces are moving is the actual direction. If I had gained a negative value here, if I had gained negative 29, this would tell me that this is moving in the opposite direction as I had first assumed. So I would need to change this direction and take it in the negative direction of Y. But since I'm having positive values for both YB and RA, it means the directions are correct. And then from here, I was always taught that you need to prove for every statistical questions. So for every statistical question that you solve, you need to prove whether the answer is correct or not. You need to prove your answer. So for you to prove your answer, you need to form an equation again for the moment at a different point. So in this case, I'll use point B since we've already used point A. So for this to be true, remember we're saying the sum of the moments at a certain point is always equal to 0. So I'll start from here. I'll say I'll stand here, and then I'll start looking at the forces. This 12 here, in this case now 12 is moving in the anti-clockwise direction, so it gains a positive value. So it will be 12 times the distance from this point here, which is times 1. When I get to Q is also moving in the anti-clockwise direction, so it has a positive value. So it will be plus Q multiplied by 1 2 plus 1.5, that is 3.5, minus RA is moving in the opposite direction, so in the clockwise direction, so it is having a negative value, so it will be minus RA times 5. This would be 12 plus Q, which is 39.5 times, sorry, Q is just 39. 39 times 3.5 will give me 136.5 minus RA. RA is 27. Sorry, 29.7 times 5. 29.7 times 5 gives me 148.5. So 12 plus 136.5 gives me 148.5. So if you subtract this is equal to 0, which is true, meaning the values that we found for YB and RA are correct. So basically this will be the first part for the question. Remember, don't forget the question. What we're being required to do here is to determine the dimensions of this cross section. So what we've done in this first video is we've determined the values that we are going to use, or the reactions that we are going to use to replace these two beam supports. So in this case, we've also determined the direction. These are both moving in the positive direction of Y, so we have this. I can now comfortably put the arrows, and then I also replace these values. I'll indicate the values here so that it becomes easy. What did we find for YB? YB, we calculated it to be 21.3 kilonewtons, and then this one is 29.7 kilonewtons. So this is the first part of our question. We've determined the forces that are in these two beam supports. Join me as we continue on this journey, as we are calculating the dimensions of this cross section. Thank you.